Hey guys, how's it going? It's Jesh here, and I'm trying out a different setup, just seeing how this works. I basically made a presentation of my own to explain one of the biggest things that organic chemistry students struggle with. So, on your first day to Organic Chemistry 2, you're gonna be faced with NMR. So, just a quick recap, NMR stands for Nuclear Magnetic Resonance, and your organic chemistry professor will go into great detail about why it's called magnetic resonance, yada yada yada. That's not important to what we want to know, we just want to know how to answer the question. Okay, so in this first video, we are going to look at the 4 different NMR graphs that are present, and I'm going to tell you what to look out for each one of the 4 graphs that you see. So let me introduce you to the 4 graphs. There's going to be a carbon-13, a proton NMR, a mass spectroscopy, and an IR spectroscopy. So first and foremost, let me rate them real quick. Carbon-13 is rated meh, proton NMR is rated really good, or good, mass spectroscopy is rated bad, and IR spectroscopy is rated ugly. So the good, bad, the ugly, and the meh. Alright, moving on to carbon-13. This is what a carbon-13 NMR will look like. It's basically just straight vertical line shooting up, and it's going from like 0 to 200 parts per million. And essentially, here are the things that you need to look out for. Carbon-13 tells you the number of carbons and the types of carbons that are present. Next, we have the proton NMR. The proton NMR looks like this, first of all. It's going to basically have different peaks, and it's going to essentially show a molecule. And it is also going to be in parts per million, but it's going to be at a much smaller scale compared to carbon. It's going to be like 0 to 5 or 0 to 10. And make sure you keep track of the y-axis. That's going to become important in a future video. So what a proton NMR tells you is, it tells you the relationship of hydrogen atoms relative to the functional groups. And this is really good because proton NMRs help to essentially answer half of the question if you're given a proton NMR. It really just depends on how sadistic your professor is. Okay, next comes the mass spectroscopy. So in the mass spectroscopy, this is what the graph that you're going to get is going to look like. Don't worry about all the other numbers, just look at the number that's on the far right and look at if it's really high. If it's the highest number, then it's most likely going to be the molecular weight of the compound. That means that you are going to have to calculate, you're going to have to come up with the empirical formula based on the molecular weight. That's kind of tricky because this is kind of useless, and it just wastes a bunch of time if you're given a mass spectroscopy. Moving on to the next one, IR spectroscopy. This one I rated the ugliest because it's very different from the rest of the graphs. However, it does give you a lot of good, helpful information. As you can see that it's not based on parts per million, it's more based on frequency. So essentially, you need to start memorizing certain trends, like this one right here is going to be an OH trend because it's a really wide gap. It's basically IR spectroscopy. If you memorize it, you use that in conjunction with either a carbon-13 NMR or a proton NMR in order to figure out the NMR question. Because an IR spectroscopy will tell you these things. It will tell you the functional groups that are present. So if you know the functional groups that are present, and you know the types of carbons and the number of carbons that are present, you can figure it out. Or if you know the functional groups that are present and you know the types of hydrogens they're attached to, you can figure out what's going on from there as well. So all in all, let me explain why I rated all 4 of these graphs as good, bad, ugly, and meh. Carbon-13 I rated meh because essentially it's just like proton NMR. It's just with an extra step. You have to look at the types of carbons instead of focusing on the hydrogens. If you have hydrogens, it makes your life so much easier. You can just go do it and boom, you're done. It's basically 50-50. 50% of your answer comes from proton NMR. The other 50 comes from infrared spectroscopy. Essentially, proton NMR would be the best thing that can happen to you in an NMR question, because if it's given to you, that means it's free points. Once I explain what the techniques are, it will make sense. Mass spectroscopy I rated bad because that one requires you to do a lot of work. You have to essentially figure out the molecular weight, then you have to figure out the empirical formula. Once you figure out the empirical formula, you have to figure out the degree of saturation. Once you figure out the degree of saturation, you have to look at your IR spectroscopy and compare it to either your proton or your carbon 13 NMRs. And then you have to figure out if you have the right number of carbons or not. It's just a lot of time consuming. And last but not least, the IR. I just rated it ugly because they could have just made all the graphs the same, but they had to make the IR one different because it's special. Just kind of bugged me, so I just rated it as ugly. But besides that, this was the first introduction to NMR and mass spectroscopy. Hopefully you guys enjoy, and I will continue on with the next video, tackling most likely Proton Nmr first. Alright, bye guys.